Hello, welcome to your lesson on creating quadratic models. What this means is creating quadratics or parabolas, equations of parabolas that match real world data or real world objects that we know have a parabolic shape. Let's take a look. We're going to look at it using Desmos, but we're also going to use our calculator, our graphing calculators to do this. So let's get started. First of all, we've learned several representations or forms of quadratic equations. One is called the general form or standard form. It looks like this, ax squared plus bx plus c. We've also looked recently at another form called the intercept form, which is basically this form factored. And once you factor it, it looks like this. We have a and then x minus m times x minus n. So these two things here help us find the x-intercepts. So those are two forms. The question is, if you were given some points, how can you create an equation of this form? So if you just knew some points of data and you knew that they follow kind of a parabola shape, how can you create the model like this, the equation to represent those points? And another question, a TOK question, how would you even choose which model to use? Which one is the one you should use and when? So let's see if you can answer that first. Okay, so let's talk about this. In order to create a model, always, we need to know, well, what's the bare minimum number of points we need to create that model? Do we need 1 point, and can we have just 1 point on a parabola and then make a good function for that? Or can we have 2 points, or 3 points, or 4 points? How many do we need to create the equation of a parabola accurately? Well, we're going to investigate this in Desmos, so let's take a look. Okay, so what I have here is we have 2 points in space. 2 points just shown on this coordinate plane. And I'll start even before a parabola, a line. Are these 2 points enough to create an equation of a line that passes through them? Well, definitely. Look, I'm going to show a line here. Look at this line. That line passes through these 2 points. So if we knew these 2 points, that is enough information to say that there is this one line and then to get the equation of that line, because there is only one possible line that passes through these 2 points. Just think about it. You could have a line going more angled, it could pass through one of the points, but it will not pass through the other. So there's only one single line that passes through any 2 points in space. So in other words, if we know 2 points and we say, what's the equation of the line? There's no confusion there. There is only one line and we can find that equation. But does it work that way with parabolas? So let's use these same 2 points and now say, okay, is there only one parabola that passes through these 2 points? Well, let's check. Here's one parabola. I already created it before. Look at that, perfect. That quadratic equation or that parabola definitely passes through those 2 points. But the question then is, okay, if I made an equation for that parabola now, would I have the single one parabola that represents those 2 points? What do you think? Well, in this case, the answer is no. Look, I have another parabola. It also passes through those same 2 points. So if somebody gave you 2 points and said, make a parabola that represents those two, you can say, well, I'm not sure. I don't think that's enough data yet. I don't have enough information to say I'm certain to find one parabola. Actually, we see 2 parabolas here, but there are infinite parabolas. Imagine this purple one shrinking down a little bit shorter, becoming narrower, and so on and so on. The green one changing also in length. You could have infinite parabolas passing through those 2 points. So the question again is, how many points? What's the minimum number of points you need to find the equation of a single parabola through those points? The answer to that is 3. I don't think I have 3 points on here, but if I had a third point, I could show you that. There's only one parabola. Imagine you had another point right here. So I'm going to put that one in just to have it. So -4, -4, 5. All right, so that parabola, now the green parabola, I'm going to close the purple one, the green one passes through those 3 points. There is no other way to draw another parabola that hits all 3 points. So if we know at least 3 points on a parabola, we can then go ahead and make an equation for that parabola. Okay, that's an important point. Let's move on from there. So here's an example of that. We have this parabola, and somebody's saying, find an equation for it. Let's make a model for that. Let's make an equation that represents that. Well, we need 3 points. We just found out we need 3 points. So what points do we know? Let's begin with the main points we know in parabolas. We know x-intercepts, for example. We know vertex also. Vertex, x-intercept, x-intercept. We've also talked about y-intercept. Of course, there's all these other points on it, but why don't we use the points that we know, these key points in a parabola? So x-intercept, vertex, and y-intercept. That's 4 points. So we can just choose 3 of those and work with those. This one we know for sure is -4, 0. We can see it. This one we know is 2, 0. This one here, the y-intercept is 0, -12. This vertex is unclear here. It looks like it's at -1 on the x, but on the y we're not sure. So let's stick with the 3 points we know for sure, which are those 3. Now that we have our 3 points, let's try on Desmos first. Okay, here's how we do it on Desmos. We're going to press plus, add a table, and add those points we know. We knew one of them is -4, 0. The other x-intercept was 2, 0. And then we had a y-intercept of 0, -12. Let me just confirm those points. Yep, looks good. Okay, so let's zoom out a little bit so I can see the 3 points. Oh, 0, there they are. So I see all 3 there. Okay, now in Desmos, we can run what's called a regression. We've done linear regression before, where we have data and we can find a line of best fit for that data by using regression. We can do quadratic regression also. So we know the general form of a quadratic is y equals ax squared plus bx plus c. So I'm going to put y1 because our data here is called y1. So y1 instead of y. And instead of equals, I'm going to use this symbol. Okay, that symbol in Desmos says let's run a regression. Okay, so ax1 squared plus bx1, and I'm using again the sub 1 because our table is x1 and y1, and then plus c. So notice I've just entered a general form of quadratic, and I've put that symbol there. It knows it ran a regression, and it told me what a, b, and c should be. So in other words, I can rewrite the equation y equals 1.5 because I can see my a value is 1.5 x squared plus b value is 3x plus, oh sorry, the c value is -12. And notice there that that parabola, I'm going to switch it on and off, and let me go to projector mode as well. Okay, those are 3 points, and that parabola, the regression model, it created that single parabola that passes through those 3 points. And again, once you have 3 points, there's only one possible parabola that will pass through them. So we have our model by regression, we found the model. Let's see how we do that on our calculator as well. Okay, because in the end, you'll be doing questions like this without Desmos using your calculator. So let's grab our calculators and let's try the 2 techniques we should be able to do. One is called quadratic regression, just like we did on Desmos. So here's the calculator. The way you run a quadratic regression on here is the same process as on Desmos. You have to first enter the data. So I'm going to do stat edit, where we always enter list data. Okay, I'm going to clear those lists because it looks like I have some other data in there. Go there, clear, enter. Okay, so I'm going to enter our 3 points. So -4, 0, I'm entering the x values first, and 2. And then the y values are 0, enter, -12, and 0. Great, I have my data in there. Now I'm going to go to stat, calc, and in calc we have all kinds of regressions. We've used a linear regression, but now we're going to go to number 5, quadratic regression. Okay, so you can either arrow down to 5 or just press 5. Okay, list 1 is our x values, list 2 is our y values, and then we go down to calculate. And it ran our quadratic regression. See, it gives it in standard form, ax squared plus bx plus c. It tells us the same a, b, and c values that we saw in Desmos. All right, and it has an r value, or that value of 1 means it's perfect. The parabola is a perfect match for that data, just like if we had a 1 for our correlation coefficient in linear correlation. Here it tells us the same thing. So there, we have our perfect parabola for that data. Okay, so let's look at the other technique on the calculator. So it created that model. We've seen that model already. Now the other way on our calculator is by using the simultaneous equation solver, something you should also be familiar with. So let's take a look. To begin this, we need to create simultaneous equations, which means a system of equations. Here's how we're going to approach that. So we're going to begin with a quadratic in general form. And then we're going to say, well, we know 3 points. So each point represents an x and y value. So for example here, using -4, 0, we can substitute for the x and y in this equation. So this is your x value, so all these two x's will become -4, right here and here, and this y becomes a 0 because that's a y value. So we've plugged that point into our equation, into our general equation, and that creates this basically an equation with three variables, a, b, and c, right? When I simplify that, negative 4 squared is 16, and then here's negative 4b, so negative 4b. So we have this equation. One equation, we can't solve that because it has three variables, but we can create another equation using the next point. So using the y-intercept, you can replace the spots in the equation as well. So negative 12 for y, the x values both become 0. So this one ends up being simpler because both of these, a and b, disappear because they're 0, so we end up with this equation. And the third equation, using the third point, we always need 3, is using this third point we know, and put that into the equation as well. 0 here, the x values are 2. That simplifies into 4a plus 2b plus c. Okay, we have three equations. Now on our calculator, we have the simultaneous equation solver, which allows us to solve systems of equations. Let me show you how to do that. So I'm going to press second quit here to go back to the main screen. We're going to go to apps. In apps, oh, I don't have it on here. Okay, I just found out that my online version here does not have that app. It does not have the poly simulation app. So let me guide you through the first couple steps, and then I have screenshots of what you should see. So you're going to look for the app called Poly Simulation 2. So PLYSMLT2. Press on that one. Okay, then you'll be like in an introductory title screen. You can press any button to go through that screen. Then it will ask you several choices. First one I think is simultaneous equation solver. Second one I think is poly root finder. So we're doing simultaneous equation solver, so number 1 I believe. Now you should be on what I'll show you is this next screen. No, not that one. Yeah, maybe this one. So once you're in simultaneous equation solver, you should see something like this. Okay, we are working with a system of 3 equations, so I think by default it's going to have 2 here, because often we just solve systems of 2 equations, but this is a system of 3 equations, so make sure this is 3 here and this is 3. 3 unknown variables, 3 equations. Once you've set that, don't worry about everything else here, you're going to press next. Next is above the graph button, so you're going to press graph to get to the next screen. So press graph, and it should bring you to a matrix. So now in this matrix, it's going to ask you to enter in the coefficients, right? In our, let me go back a couple screens. We have our 3 equations here, 1, 2, and 3. So in the matrix, you're going to enter in these values in order, 16, negative 4, and then here's a 1 in front of the c. And then you're going to enter here in this equation, we don't have an a and b, so you're going to put 0 for a, 0 for b, and then 1 again for c. And then the last equation, we're going to have 4, 2, and 1. So make sure you have these equations on hand, and let me go back to that screen now. So let's look here, right? We had 4, 2, 1, and then after this line here, you're going to put what that equation equals. So the first equation was equal to 0, right? And the next equation, the coefficients were 16, negative 4, 1, and is equal to 0. I guess that was our third equation. And the second one had the coefficients on A was 0, there was 0b, and then there was 1c, and that equaled negative 12. So I hope by looking at your equations and looking at this matrix, you can see clearly what's being entered. You're just basically entering the numerical values from your equations. Once you've entered that, it has your system of 3 equations input. It is ready to solve. So you're going to press solve, which means the graph button here again. Press graph, it will solve it for you, and it will produce your 3 values, your 3 coefficients. So basically it found the solution to your system. It found an answer for what A should be, B, and C. It found your answers for A, B, and C, the 3 variables. And that matches exactly what we had before when we did the regression. Those are the exact parameters that our quadratic equation should have, resulting in this one here. So now you know 3 methods. Let's try them out. Let's see if you can do it. So for these 3 problems, you're going to use method 1, which is the regression method that we just saw, by entering data into lists and finding that. So here's 3 parabolas. Find the exact equations for each of these 3 by using 3 points, and using x-intercepts, and a vertex here is a good idea, and here maybe x-intercepts and a y-intercept is a good idea. Here we have x-intercepts and vertex is clear, right? So find those clear points first and then use the regression method. Here's the first one, here's the next one, here's the third one. Okay, now for the next 3, use the simultaneous equation solver method, the one we just looked at with the matrix and all that, using the app poly simulation. Okay, here's the 3. Again, pick 3 points that you know for sure first, and then use the simultaneous equation solver. So here's that answer, here's this one, and here's this one. I hope it went all right. If you followed the process, you should know it. There's another video. Please watch it now.